Assalamu alaikum. In this virtual class, I will be discussing, or rather I will be teaching decimation frequency FFT algorithm. Now, if you remember x of k can be written as summation n running from 0 to n minus 1 x of n w of n k, right? So what I want to do now is I want to break this summation into two equal parts. So I can rewrite this summation as summation n running from 0 to half of this will be n by 2 minus 1 x of n w of n kn plus summation. So what is the next sample after n by 2 minus 1? That is n by 2 minus 1 plus 1, that is n by 2. So that will be n running from n by 2 to the last of the summation is n minus 1 x of n w of n k n, fine. So in this summation, if we notice that the limits of summation are from n running from n by 2 to n equivalent to n minus 1, and in this it's from 0 to n by 2 minus 1. What I want is that the limits of the summation should be same in both of the summations. So basically in the second summation I want that the limits should be from n running from 0 to n by 2 minus 1. So for this, what I will do, I will replace n with n plus n by 2. Okay, so and then this implies k will be equal to summation n running from 0 to n by 2 minus 1 x of n w of n kn plus summation. So here it will be n plus n by 2 equivalent to n by 2 to limits n plus n by 2 equivalent to n minus 1. Here I will place x n plus n by 2 w of n instead of k, instead of n I will write n plus n by 2. Okay. So in this summation now, in this limit, if I move n by 2 on this side, it becomes n by 2 minus n by 2 is equal to 0. That then it means n will be equivalent to 0. And on the upper limit, if I move n by 2 on this side, then it becomes n by 2 minus 1. So n becomes equivalent to n by 2 minus 1. So on the lower limit I get 0, and on the upper limit I get n by 2 minus 1. Same as the case of the first summation. So I can write this as summation n running from n by 2 minus 1 x of n w of n kn plus summation. This will be equivalent to n running from equivalent to 0, that's n by 2 minus n by 2 to n by 2 minus 1 x of n plus n by 2. So I'll just break it down. This becomes w of n kn into w of n k into n by 2 k n by 2, fine. So if I take this value, this is w of n k n by 2, fine. So this will be w of n is equivalent to e raised power minus j 2 pi by n, fine. So this is being multiplied by kn by 2. So it's multiplied by kn by 2. So n and n cancels out. So this is equivalent to e raised power, also 2 and 2 cancels out. So it's e raised power minus j by k, fine. can write this as e raised power minus j pi whole raised power. Okay, so this becomes cos of pi minus j sine of pi whole raised power. Okay, so this becomes cos of pi is -1, this is 0 whole raised power. Okay, so this becomes -1 raised power. Okay, so instead of this wn kn by 2, what I can write -1 raised power. Okay, fine. So we'll go to the next page. So I will substitute this in, say, in the x of k. So I will get x of k will be equivalent to summation n running from 0 to n by 2 minus 1 x of n w of n k, and this is my first summation. We have done nothing with this. Change are in the second summation, 0 to n by 2 minus 1 x of n plus n by 2, and then w of n kn, and instead of w of n kn by 2 we will write here -1 raised power k. Now this -1 raised power k is independent of the summation, so we can write it outside. Also, if you see in both these summations, that is this summation and this summation, the limits are same, so we can combine them. So this becomes summation n running from 0 to n by 2 minus 1. I can write x of n plus x of n plus n by 2, right, into -1 k, and the common term is wn. Okay, right? So this is my x of, okay, fine. So now this x of k, as in case of DIT, what we used to do, divide in that case we used to divide x of n into even and odd parts. Now here we will divide x of k into even and odd parts. So what we will do, we will divide them into even and odd, right? So I will have x of k equivalent to x of, I'll write 2k is for even, and 2k plus 1 will be for odd, fine. So this is my even samples, and this is my odd samples, fine. So now I'll write equation for x of 2k and x of 2k plus 1, right? So let me write it for x of, I will try to manage them in a single page. X of 2k will be equivalent to summation n running from 0 to n by 2 minus 1. Right? So then I have open brackets x of n plus n by 2 minus 1 raised to 2k, brackets close, wn 2k. So what I have basically done here, I have replaced k with 2k. So we had a -1 raised to k here, so we had written -1 raised to 2k here. Here we had wn kn, so instead of k we had written 2k here. Rest remains the same. Similarly, for 2k plus 1, x of 2k plus 1, we will replace k with 2k plus 1. So x of 2k plus 1 becomes summation n running from 0 to n by 2 minus 1 x of n, bracket start, plus x of n plus n by 2, right? Then -1 raised to 2k plus 1, right? Brackets close, wn, so 2k plus 1 multiplied by n, right? So let's name them. Let's name this as first and this as second, right? So now let me go to the next page. So now in this case, in case of x of 2k and x of 2k plus 1, what is the range of k? The range of k, since I have divided x of k into two sequences, that is x of 2k even sequence and x of 2k plus 1 odd sequence. The original range of x of k was k running from 0 to n minus 1. So but now I have divided it into two sequences having equal number of samples. So the range of k here will be k running from 0 to n by 2 minus 1 in case of x of 2k, and in case of x of 2k plus 1 it will be same, that's k running from 0 to n by 2 minus 1. So the range of k is from 0 to n by 2 minus 1 because of division of x of k into equal length sequences. Fine. Okay. So range of k in both the cases, x of 2k and 2k plus 1, will be 0 to n by 2 minus 1. Similarly, range of n is as given in the summations, it is 0 to n by 2 minus 1. So if capital N is equal to 8, then range of k will be from 0 to 4, and range of small n will be from 0 to 4. Fine. Now let's consider 4 cases. If we see these two equations, that is x of 2k and x of 2k plus 1, where variables minus 1 raised to power 2k, minus 1 raised to power 2k plus 1, we have wn 2kn and wn 2k plus 1n. So we will try to solve these 4 things. So now if we come to the first one, that is minus 1 raised to power k, right? Minus 1 raised to power 2k, sorry. So this is equal to I can write it as minus 1 square, right, whole raised to power k. So minus 1 square will be always equal to 1. So 1 raised to power k, this will be equal to 1. Since k can take any values from 0 to integer values, so 1 raised to power k will be equal to 1. So next I have minus 1 raised to power 2k plus 1. So I can break it down. It will be minus 1 raised to power 2k into minus 1 raised to power 1. I know minus 1 raised to power 2k is 1, so this will be 1 into minus 1 raised to power 1 is minus 1, so 1 into minus 1, so this will be minus 1. Fine. So let's name this 3, let's name this 4. So then we have wn 2k n. Fine. So this will be equal to wn is equal to e raised to power minus j 2 pi n. Fine. So I will multiply it by 2k n. So what happens here? So this will be equivalent to this 2, this is multiplied by 2, so I can write it as n by 2. So I will write it as e raised power minus j 2 pi, fine, into kn divided by n divided by 2. Fine. So this is nothing. this e raised power minus j2 pi. So this is w, I can write as w n by 2. Okay, I guess we have also done it previously, but still. So this is equation 5. Now let me come to w n 2k plus 1. This is w n, I will break it down into 2k, w n raised power 1, 2k plus, sorry, this is n here, huh? So I'll write 2k n, and here it will be. So we know w n 2k n is equal to w n by 2, fine, k n into w n. So I have derived this from equation 5. So I will name it as equation 6. So we have four equations, 3, 4, 5 and 6. So I will substitute it in 1 and 2. 3 and 3 and 5 in equation 1, and 4 and 6 in equation 2, right? So what I will get x of 2k will be equivalent to summation n running from 0 to n by 2 minus 1 x of n. Then we had minus 1 raised to power 2k here, plus minus 1 raised to power 2k here. So instead of that I will get 1. So I'll write plus 1 multiplied by x of n plus n by 2. So this is multiplied here, and then whole thing was multiplied by wn 2k. So this instead of wn 2k and I will write wn by 2. Okay, fine. So this, let me say this is this is 7, right? And now let me go to next page. So now I have to find x of, using substitution, x of 2k plus 1, that will be summation n running from 0 to n by 2 minus 1 x of n. So now we had here minus 1 raised to 2k plus 1, that was equal to minus 1. So I will write minus sign here. So the minus sign will be x of n plus n by 2. Fine. And then we had wn 2k plus 1 into n here. Wn raised to 2k plus 1 into n. So this term will change to w n by 2 k n multiplied by, we have a multiplication term here, wn raised to small n. And so let's name it as 8. Fine. So I can write this x of 2k plus 1 as summation n running from 0 to n by 2 n by 2 minus 1 x of n minus x of n plus n by 2. I can bring this wn inside these brackets. So I will just close this bracket first. So this will be wn raised to power n multiplied by wn by 2. Okay, that means this is 7. Fine. So in this was 7, right? This was 7 x of 2k, that's in part, and this is for x of 2k plus 1, that's odd part. So in this case, let me do some substitutions. So let's assume g1 of n is equivalent to x of n plus x of n plus n by 2. And g2 of n is equivalent to x of n minus x of n plus n by 2 whole multiplied by wn. Okay. So this is 10, this is 11. So 10, I will substitute 10 and 11, 10 and 11 and 7 and 8, 7 and 9, sorry. So I will get x of 2k equivalent to summation n running from 0 to n by 2 minus 1 g1 of n w of n by 2 raised for kn and x of 2k plus 1 equivalent to summation n running from 0 to n by 2 minus 1 g2 of n wn of 2 raised for k. Fine. So let me name them as 12. This is 13. These two are right. So now let me go to page number 5. So what we have done is that now let's assume, let's take an example. Let's assume capital N is equal to the sum of samples we have taken as some problem here because okay. So what I've done, I've taken it as 8. So this means now two sequences g1 of n will be equivalent to then x of n, fine, plus it's equal to x of n plus x of n plus n by 2, fine. And this, and the range here will be 4 n running from 0 to n by 2 minus 1. Why? Because g1 n and g2 of n, there are two subdivisions of x of n. So in x of n, number of samples is n. So in case, so they are equal subdivisions, equal length subdivisions. So in case of g1 of n, number of samples will be n by 2 minus 1, 0 to n by 2 minus 1, that's n by 2. In case of g2n, number of samples will again be n by 2. So let me substitute. In our case n is 8, so n by 2 is 4. So I will go with g1 of, so g1 of n will have 4 samples, g1 of 0, g1 of 1, g1 of 2 and g1 of 3. So g1 of 0 will be equivalent to, so substitute n equals 0, there will be x of 0 plus x of 0 plus n by 2 is 4. That's x of 0 plus 4. So that will be equivalent to x of 0 plus x of 4. Right. So next I will be having g1 of 1, that will be equivalent to x of c1 n equivalent to 1 plus x of 1 plus 1 plus n by 2 is 4 plus 1 is 5, so that will be x of 5. Similarly g1 of 2 will be equivalent to x of 2 plus x of 6, and g1 of 3 will be equivalent to x of 3 plus x of 7. Fine. So this is for g1 of n. Now in case of g2 of n, g2 of n equation is g2 of n is equivalent to, this is the odd sequence, gx of n minus x of n plus n by 2 whole multiplied by wn raised to power n. Right. So we will substitute n equal to 0, 1, 2 and 3. So we have g2 of 0 equivalent to x of 0 minus n is 0 here, so 0 plus n by 4 is 8 by 4 is, sorry, 8 by 2 is 4. That becomes x of 4 whole multiplied by w, n is, capital N is 8, w 8, and small n we have substituted it as 0, that is w8 0. Similarly g21 will be equivalent to x of 0, sorry, it will be x of 1 because n has been substituted as, it will be x of 1 x of 1 minus x of n is 1 plus n by 2, that is 4, that is 5, and we multiplied by w, n is 8. So that will be w8 1. Fine. Similarly I can write g22 as x of 2 minus x of 6, w8 2, and finally the, I can go to the next page, page number 6. And g2 3 as, that will be x of 3 minus x of 7 whole multiplied by w8 raised to 3. Fine. So I have drawn this after substituting the values of g1 of n and g2 of n. We have 4 values of g1 of n, and similarly we have 4 values of g2 of n. Now coming to the g1 of 0. g1 of 0 is equivalent to, if we look at this, it is equivalent to x of 0 plus x of 4. So x of 0, that's here the first line, plus x of 4. So we simply have a summation between x of 0 and x of 4. Similarly g1 of 1 will be equivalent to x of 1 plus x of 5. So a summation here. Fine. So and then g1 of 2, it's equivalent to x of 2, fine, this line, plus x of 6, and g1 of 3 is equivalent to x of 3 plus x of 7. Now coming to g2 of 0. g2 of 0, this is equivalent to x of 0 minus x of 4 whole multiplied by w8 0. So x of 0 is this line, x of 0, this term here, minus x of 4. So this is x of 4, so we'll simply multiply it by minus 1 because there is summation here. So minus plus becomes minus, so this becomes x of 0 minus x of 4. Still we have not got g2 of 0. We need to multiply it by w8 0. So here a multiplication by w8 0. So the term here becomes x of 0 minus x of 4 multiplied by w8 0. Similarly, g2 of 1 is equivalent to x of 1 minus x of 5. So a multiplication by minus 1 here, and then a summation. So so the term here is x of 1 minus x of 5. So we multiplied by w8 1 to get g2 of 1. Similarly, we get g2 of 2 and g2 of 3. So basically what we have got, g1 of n, this is a 4-point sequence, and g2 of n, this is a 4-point sequence. So we'll have to take 4-point DFTs to obtain x of 2k and x of 2k plus 1. Now we need to break down this 4-point DFT into subdivision, subparts. So we'll see that in the next class. I'll stop here.